Hello everyone, this video tutorial introduces the application of automated workflow for aquatic toxicity to fish. Toolbox functionalities have expanded over the years, making the system more complex, especially for inexperienced users. In this respect, automated workflows for predicting toxicological endpoints have been developed. The workflows are designed to generate reliable predictions based on a predefined algorithm. The algorithms include application of specific profilers, data sources, and data gap filling techniques depending on the endpoint for which they have been developed. The aim of this video is to demonstrate the automated workflow for predicting aquatic toxicity to fish. Before the demonstration, the theoretical background of the workflow is presented. The endpoint covered by the automated workflow is LC50, the effect is mortality, and the test organism is fish Pinephales promolus. The algorithm of the automated workflow includes the main modules and actions of the toolbox workflow needed to generate a prediction, such as profiling, category definition, and data gap filling. The input and report sections are not part of the automated workflow, which means that the user must enter the chemicals of interest and when predicted to generate the report. A schematic illustration of the aquatic workflow can be seen here. Once the target chemical is entered into the system and the workflow is started, the system automatically defines the target endpoint and identifies the structural characteristics and possible mechanisms of action of the target to be used for the collection of analogs. This is done by simultaneously applying the profilers relevant to the target endpoint and additional criteria to select the profiler containing the most populated category of chemicals and data for the primary grouping. Further, the workflow proceeds with data gap filling. Depending on the number of analogs within the primary group, the workflow continues with a trend analysis or read-across approach. If the number of analogs is over 10, trend analysis is used, otherwise the read-across is used. The primary group of analogs is further refined by a sequence of subcategorizations, again relevant to the target endpoint. First, chemicals that have a different substance type than the target chemical are eliminated. Second, chemicals whose Euclid presentation differs from their test material are removed. The third subcategorization is the elimination of chemicals whose LC50 data are greater than their water solubility, obviously some artificial data points. Finally, structurally dissimilar chemicals are eliminated by a list of profilers. There are also criteria for acceptability of the prediction. The coefficient of determination must be greater than 0.7 and the number of analogs must be greater than 10. If these criteria are not met, the workflow automatically switches to the read-across approach. The same sequence of subcategorizations is applied as in the trend analysis. Finally, the read-across prediction is checked for acceptability based on three criteria: variation of LC50 and log count of the nearest analogs must be less than 2 log units and the number of analogs must be higher than 5. If the criteria are not met, the target chemical is not predicted. Now let's start with the example. Enter the chemical with the identification number 111-86-4. Go to the Data Gap Filling section, where the section with the available workflows is located, and click Automated. A list of automated workflows appears. The automated workflow for predicting aquatic toxicity to fish is the first in the list. Detailed descriptions of the workflows in this list can be found at the question mark button. To execute the workflow, you must click on the Run button. The View button provides a schematic illustration of the logic execution. The button Run on Server executes the workflow on the server side only, without displaying the steps performed during execution. The process is fast and is suitable when a large list of chemicals needs to be predicted. Let's run the workflow. The decision tree with algorithm is displayed. The system automatically applies each of the steps described in the theoretical background. In addition, the execution of the workflow leads to the construction of the document tree, with each action creating a corresponding level in the tree. Using the respective buttons, we can stop, pause, resume, or wait for the workflow to complete. A message appears with predicted value. Confirm the message and close the window. Now we have a prediction for the target chemical that can be exported or reported in different file formats. Similarly, the workflow could be applied to a list of chemicals. To do this, create a new document and load a file from the example folder. Go to the Gap Filling section and click on the Automated button. Select the workflow and run it. There are options that control how the workflow should be executed. The first option allows a specific range of chemicals to be selected in the list for predictions by the workflow. In our case, we set it to 1 to 10. By default, another option is enabled that controls the propagation of document tree levels. This has been implemented to save memory in case a large number of chemicals are submitted for predictions. Click on the OK button. When the workflow is complete, a pop-up message appears on the screen. Congratulations! Now you are ready to learn more about the functionalities in Toolbox and how to use them. Contact QSAR Toolbox Help Desk for technical questions. If your question concerns policy or regulatory acceptance of Toolbox results within the EU legislations of ECHA's competence, please refer to the ECHA website directly.